In the year 2151, the Klingon Empire, the name that might ring a bell to Star Trek fans, received the world's first photon torpedo, a weapon of unimaginable destruction. The proton torpedo, a catastrophic weapon of mass destruction, has intrigued real-world scientists. This hypothetical explosive would vaporize anything within an 11.5-kilometer radius, a terrifying concept that's now being seriously considered. So, what if Star Trek science fiction becomes a reality? Hello and welcome back to Lux Underground. Many concepts, once considered pure fantasy, are now our reality. Think of mobile phones, surveillance cameras, or solar batteries. With this in mind, it might not be far-fetched to think that one day we might understand or even harness the power of photon torpedoes. Sounds impossible. Maybe not. The science of photon torpedoes. Let's get into the captivating science behind photon torpedoes. Essentially, their raw power is due to the interaction between atoms and antiatoms. When these opposite entities come into contact, annihilation occurs, releasing an astronomical amount of energy. This reaction forms the basis for the dramatic destructive explosions we've come to associate with these sci-fi powerhouses. To put this into perspective, let's draw a comparison. The explosion of a photon torpedo, as depicted in Star Trek, would release an energy equivalent to around 50 megatons of TNT. That's staggering considering the Tsar bomber, the most powerful nuclear bomb ever detonated by mankind, released about 58 megatons of energy. The Tsar bomber was detonated by the USSR over Novaya Zemlya on October 30th, 1961, and the mushroom cloud it generated rose to a height of 67 kilometers. The Tsar bomber weighed a hefty 26.5 tons, roughly the weight of 7 adult African elephants. On the other hand, a photon torpedo is significantly lighter, weighing only about 250 kilograms. This stark contrast raises some fascinating questions about the efficiency and potential impact of such a weapon if it were to move from fiction to reality. The feasibility of building a photon torpedo. But could we actually build a photon torpedo? The science behind it seems straightforward, but the practicality is a whole different ballgame. In the Star Trek universe, photon torpedoes weigh only 250 kilograms, making their deployment significantly easier than traditional nuclear bombs like the colossal 26.5-ton Tsar bomber. The main challenge comes from the antimatter itself, the key ingredient for the explosive power of the photon torpedo. In reality, we're only scratching the surface of harnessing antimatter. In 2010, scientists from the European Organization for Nuclear Research, known as CERN, made a significant breakthrough. They captured antimatter for the first time in history, managing to hold 38 anti-atoms for 172 milliseconds by cooling them to minus 73 degrees Celsius. By the next year, they were able to hold 309 antiprotons for about 17 minutes. Yet, this is just a drop in the ocean compared to the 1.5 kilograms of antimatter required for a photon torpedo. There's another catch. Antimatter isn't just difficult to harness, it's also mind-bogglingly expensive to produce. Just 1 gram of antimatter costs a staggering $63 trillion, making it the most expensive substance on Earth. The future of antimatter and photon torpedoes. Looking ahead, the future of antimatter and photon torpedoes is intriguing, even if a bit uncertain. Currently, our ability to produce antimatter is limited. We've only harnessed a minute amount, nowhere near the 1.5 kilograms needed for a photon torpedo. Yet, advancements in technology and scientific understanding could change that. One promising area is the propulsion system of a photon torpedo, known as the warp drive. This mechanism allows the torpedo to travel at near light speed, 225,000 kilometers per second to be exact. That's 3/4 the speed of light. The implications of such speed are staggering. Consider this: if we were to launch an object as heavy as a large rock at this speed, the impact would be catastrophic, potentially equivalent to a massive explosion. However, moving at the speed of light isn't without its challenges. To achieve this, an object needs to have zero mass, a property that's currently exclusive to photons. This is a significant constraint considering that all known spacecraft have mass. A solution to this quandary lies in bending space-time around a spaceship, a theory put forward by Mexican physicist Miguel Alcubierre in 1994. With such a warp bubble, an object with mass could theoretically move faster than the speed of light through space and time. There are also exciting developments in quantum teleportation. Scientists are learning more about the nature of spatial wormholes and have even managed to teleport quantum particles over long distances. This sounds like something straight out of Star Trek, but it's happening in our labs today. One example of this occurred in 2020 when a team of physicists in China managed to teleport quantum information between two entangled particles over a staggering 44 kilometers. This was an unprecedented feat that seemed to defy our traditional understanding of physics. The team used a process known as quantum entanglement, a phenomenon where two particles become inextricably linked, and any changes to one particle will instantaneously affect the other regardless of the distance between them. Moreover, scientists are now exploring the concept of spatial wormholes, passages through space-time that could create shortcuts for long journeys across the universe. Theoretical physicist John Wheeler once stated, "Wormholes are merely the consequence of the field equations of the theory of general relativity." Though we are yet to observe or create a stable wormhole, the groundwork laid down by Einstein and subsequent research has opened up a world of possibilities. As our scientific understanding expands and our technology evolves, who knows what the future holds? Perhaps a photon torpedo isn't as far off as we might think. The possibility of space-time manipulation. Building upon our understanding of the limitations and potential of photon torpedoes and antimatter, it becomes intriguing to imagine what we could achieve if we could manipulate the very fabric of space and time. This possibility is introduced through the concept of bending space-time around a spacecraft. This theory is named the Alcubierre drive, after Mexican physicist Miguel Alcubierre. In 1994, he postulated that by creating a warp bubble around a spacecraft, we could compress space in front of the bubble and expand it behind. This concept, drawn from Einstein's theory of general relativity, would essentially allow the spacecraft to traverse vast distances in a fraction of the time it would usually take, seemingly breaking the cosmic speed limit. Alcubierre's model envisages a spacecraft situated within a warp bubble, stationary in its own frame of reference, while space itself moves around it. It's like moving a carpet while an object on it stays still. This would theoretically allow the whip to reach a destination faster than light traveling in normal space. However, the implementation of Alcubierre's theory comes with challenges. One of the most daunting is the requirement of negative energy density, something synonymous with antimatter. The energy required to form an Alcubierre drive is currently beyond our reach. According to some calculations, it would necessitate an amount of antimatter equivalent to the mass of Jupiter. This monumental requirement is what makes practical application of the Alcubierre drive a matter of future scientific advancement. Yet the history of science is filled with seemingly insurmountable challenges that were eventually conquered. Michael Faraday once said, "Nothing is too wonderful to be true if it be consistent with the laws of nature." While the Alcubierre drive remains theoretical today, continued advancements in physics and our understanding of antimatter could someday bring this theory to fruition. Ultimately, the Alcubierre drive offers a tantalizing promise: the ability to traverse the cosmos without being restricted by the speed of light. While the technical requirements are formidable, it remains a beacon of what we could potentially achieve. an affirmation that our future exploration of the cosmos might not be bound by the light barrier after all. Current research on space-time manipulation. With an understanding of the theoretical prospects for space-time manipulation, we turn to NASA's EagleWorks laboratories and leading academic institutions. NASA's EagleWorks has been pushing the envelope seeking practical applications of the Alcubierre drive theory, while university labs delve into the mysteries of quantum mechanics and wormholes. Among these efforts, a standout achievement comes from a team led by Maria Spiropoulou at Caltech and Daniel Jafferis at Harvard University. Their goal wasn't modest: to create a system that mimics teleportation through a wormhole, initially faced with a major hurdle, the daunting requirement of a high number of qubits, far exceeding the capacity of current quantum processors. They turned to machine learning to unravel a solution. Through this approach, they identified the minimal number of qubits needed and the optimal coding for the quantum teleportation protocol, enabling the experiment to run on just 9 qubits with 164 2-qubit gates on a Google Sycamore quantum processor. In their groundbreaking experiment, the researchers managed to keep a wormhole open long enough for practical use by applying negative energy shockwaves, special pulses of quantum fields that function as a sort of cosmic defibrillator. Then, they studied how the quantum information behaved in this extraordinary setup. Remarkably, the signals sent through the wormhole underwent a complex process of scrambling and unscrambling, but the quantum information emerged from the wormhole untouched. This research serves as a monumental stride towards realizing the promise of space-time manipulation, the future of space exploration. As we cross the frontier of our understanding of the universe, the future of space exploration holds infinite promise. The ability to manipulate space-time could completely redefine how we venture into the cosmos. With the advent of the Alcubierre drive, interstellar travel may no longer remain the stuff of science fiction. We could traverse vast distances in the blink of an eye, making these exploration efficient and more achievable. But the potentials of this new era extend beyond exploration. Photon torpedoes, once viewed solely as destructive devices, could have profound peaceful applications. We could use these devices as high-energy probes to study distant cosmic phenomena, shedding light on the mysteries of the universe. Such advancements in technology could also bring us closer to the tantalizing possibility of contact with extraterrestrial life forms. As we stand on the precipice of an exciting new era in space exploration, we must ponder: are we ready for the challenges and opportunities that unlocking the secrets of photon torpedoes and space-time manipulation could bring? That's all we have for you today. Don't forget to like and subscribe to our channel for more amazing content. We'll be back soon.